All right, let's get right into it. And I promise, this is not going to be some scary high-level physics lecture. What we're talking about today is the fundamental rulebook for the entire universe. And these aren't just, suggestions. They are the absolute unbreakable laws that govern everything, from how a star shines to why your coffee gets cold. It really all boils down to questions like these, doesn't it? Super simple, everyday things that you've probably wondered about at some point. And believe it or not, the answer to both lies in the very same cosmic set of rules. These laws are happening all around you, all the time, and today we're going to pull back that curtain and see exactly how they work. So here's our game plan. We're going to walk through the 4 laws of thermodynamics, one by one. But I want you to think of them less as laws and more like the rules of a game, the game of existence itself. We'll start with the rule that basically sets up the playing field, and then we'll get into the 3 big ones that you can never, ever beat. Let's kick things off with a law that's so fundamental they actually had to add it in before the first one. Kind of funny, right? This is the Zeroth Law, and it's the one that establishes the very language we need to even start talking about energy and heat. You can call it the rule of agreement. Okay, I know what you're thinking. That sounds incredibly obvious, right? It's basically the transitive property you learned in math class. But this simple-sounding rule is what makes temperature a consistent, measurable thing across the entire universe. It establishes this critical concept called thermal equilibrium, that moment when no more heat is flowing because everything's reached the same temperature. I mean, think about it. When you stick a thermometer under your tongue, what happens? You wait, and the reading eventually stops changing. That moment, that's thermal equilibrium in action. The Zeroth Law is the cosmic guarantee that the temperature the thermometer is showing is a reliable measurement of your temperature. Without this law, the whole idea of temperature would just fall apart. Okay, so now that we have a language for temperature, let's move on to the next rule. Welcome to the first law of thermodynamics, which you can sum up really easily with a simple gambling rule. You can't win, period. You can't get something for nothing. This is the universe's strict accounting principle. This might be one of the most famous sentences in all of physics. It's the law of conservation of energy. What it means is that the total amount of energy in a closed system, and you can think of the universe as the ultimate closed system, is constant. It can move around. It can change from chemical to heat to motion, but the grand total never, ever changes. And yep, here's the math that proves it. But don't let the letters scare you off. All this equation is really saying is that energy is like money in a bank account. The change in your balance, that's delta U, is just the deposits you make, which is the heat you add, minus your withdrawals, which is the work the system does. Every single bit of energy has to be accounted for. No exceptions. So what does this actually mean for us? Well, for one, it's why every single attempt to build a perpetual motion machine has failed, and always will fail. You just can't get work out without putting some energy in. It's also why your phone gets warm when you use it. That electrical energy from the battery doesn't just disappear. It gets converted into running your apps, lighting the screen, and yeah, a lot of it becomes waste heat. The universe's books are always balanced. All right, so if the first law says you can't win, the second law is even tougher. It says you can't even break even. This one is probably the most profound and mind-bending of all the laws, because it doesn't just track where the energy is, it tells us which way it has to flow. It gives us the arrow of time itself. The law itself is pretty simple to state, but it contains one of the most misunderstood concepts in all of science: entropy. It just says that for any process that happens on its own, the total entropy of the universe either increases or at best stays the same. It never, ever goes down. So the big question is, what in the world is entropy? We often hear entropy described as just disorder. A messy room has more entropy than a clean one. And look, that's a decent starting point, but it doesn't tell the whole story. A much better, more accurate way to think about it is as energy dispersal. Entropy is really just a measure of how spread out, how diluted, how, useless that energy has become. And nature always, always moves from concentrated, useful energy to spread out, less useful energy. And you see this everywhere, every single day. Heat naturally flows from your hot cup of tea into the cooler air of the room. The energy disperses. It never spontaneously flows from the cool room back into your cup to make it hotter. If you spray perfume, those molecules spread out to fill the entire room. They don't huddle together in a neat little clump. That right there is the relentless, unstoppable march of entropy. And this is why time only moves in one direction. It's why we remember the past, but not the future. Because the universe is constantly moving towards a state of higher total entropy. Think about it. You can break an egg, but you can't unbreak it. The process is irreversible, because that scrambled state is a much higher state of entropy. Just like that egg, the universe itself is on a one-way trip from order to disorder. The second law is the ultimate reason why. So, to recap, you can't win. And you can't even break even. Well, the final rule of this cosmic game is this. You can't quit. You're not allowed to just stop playing. The third law sets an ultimate limit, a coldest possible point that you can get tantalizingly close to but can never, ever actually reach. So that's a formal statement. It beautifully connects our last two big ideas, temperature and entropy. What it's saying is, as you get colder and colder, heading towards the absolute minimum possible temperature, the entropy, that energy dispersal, of a perfectly ordered substance also drops down to its minimum value, 0. And here it is, absolute 0. 0 on the Kelvin scale. At this impossible temperature, all the random jiggling and vibrating of atoms would just stop. It would be a state of perfect order, minimum energy, and 0 entropy. A state of absolute, perfect stillness. But here's the cosmic catch. You can never actually get there. It's what's called an asymptotic limit. Scientists have gotten unbelievably close. We're talking billionths of a degree. But reaching absolute 0 is physically impossible. As the system gets colder, it becomes exponentially harder to pull out that last little bit of heat. It's like nature itself fights back, making sure you can never fully quit the game. So let's just take a step back for a second and look at the absolutely beautiful structure these 4 rules create. They're not just some random list. They form this complete, elegant, and logical architecture that describes how the physical world works on every single scale. So here's the lightning round recap. The Zeroth Law, it makes temperature a real, measurable thing through equilibrium. The first law is all about the conservation of energy. You can't create or destroy it. The second law is about entropy always increasing and energy spreading out. And the third law defines that bottom limit, absolute 0, a point you can never reach. But maybe an even better way to think of them is like this. The Zeroth Law is the language. It gives us the words to talk about heat and cold. The first law is the universe's meticulous accountant, making sure not a single joule of energy ever goes missing. The second law is the deep philosopher, the one that tells us why time flows forward and not backward. And finally, the third law is the surveyor, marking a fundamental boundary of reality that can never, ever be crossed. So together, these 4 laws form this elegant and completely inescapable framework. Everything from you making a cup of coffee to the entire life cycle of a star has to follow these rules. And that leaves us with one final and kind of chilling question to think about. If the second law is true, and the total entropy of the universe is always increasing, what does that really mean for the distant, distant future? What is the final state that these cosmic rules are pushing all of us towards?